Dulu.
Atau
Cek,
bagaimana?
cek. Oke, sip. Kita mulai. Ini matkul apa tadi tuh? Special topics in physics. Berapa menit katanya presentasinya? Kenapa malah ini?
Nggak tahu. Kau dengar suara saya enggak?
Dengar.
Oke, jadi hari ini saya akan mempresentasikan tentang quantum integrable system.
Pakai bahasa Inggris lah latihannya.
Yeah, today I want to talk about
Oke,
quantum apa?
good lah udah lanjut next. Proceed.
Okay, good morning everybody. My name is Aziz Albarofi Darajat. Today I want to talk about quantum integrable system. What is quantum integrable system? Before we going quantum, I think we should talk about the classical integrable system first to have an basis or analogy of the integrable system. So classically, before that, classical integrability. So if we have two n-dimension phase space, what is phase space? Phase space is a space that contain all the configuration of the classical system. So you have two n-dimensional phase space. Then the system called classically integrable if we have n number of integral of motion. What is integral of motion? So integral of motion is a quantity or a function that satisfy this equation. So Q H equal dq equals 0. So a quantity or a function is called integral of motion if the Poisson bracket of that quantity is 0, or it is doesn't depend on time. Not only we need n number of integral of motion, we need that the integral of motion is also involutive. I will add an I index there because we have n number of integral motion. So what is involutive? Involutive means that all of the integral of motion is the Poisson bracket of all of the each integral of motion is 0. J equals 0. Okay. Yeah, so this is the definition of classical integrable. What is the consequence of the classical integrable? If a system is classical integrable, then we can find the exact solution of that system. Or we say that the system is exact solvable because we can find the exact solution. Why we can do that? Because the system have a lot of symmetry because of the integral of motion, and the system is highly constrained because of that symmetry, and because of that highly symmetrical system, then it is too easy to find the solution. Yeah, not easy, but we can find the exact solution. So there are another structure that we can impose to classical system to find its integrability. It's called Lax pair. So what is Lax pair? Lax pair is a pair of a matrix. We call the matrices L and M. And the matrices satisfy the Lax equation. That is, the derivative of L is equal the commutator of M and L. So what is the consequence of Lax pair? If we have Lax pair, then we can build the all of the integral of motion in that system. So the integral of motion, we can find it by calculating the trace of the one of the Lax pair matrix. But the problem is Lax pair is hard to find. There's no systematic way to find the Lax pair. And I won't say how to find. I just say there's no systematic way to find those pair. So it is purely like ansatz. the dimension of the matrix, square matrix, yeah. Is not necessary related to the dimension of the system. Also, it is not unique. But if we can find Lux pair, then we can build the integral of motion of the system immediately. But to call the system is integrable, we don't just need the integral of motion, we need that the integral of motion also involutive. So those condition is translated into this equation. Where R12 is called classical R matrix, classical R matrix. And L1 is L tensor product with identity, and L2 is 1 tensor product with L. So L is element of endomorphism of EV, and the R12 is also R12, L1, L2. All of that is element of endomorphism of VV, where V is the vector space of the Lux pair matrix. So the quest to find the integrability structure is changed to find the Lux pair and the R matrix. So if we can find those two things, Lux pair and classical R matrix, that satisfy this equation and this equation, then our system is classically integrable. Now we move to quantum integrability. What is quantum integrability? Actually, there's no accepted definition of quantum integrability, but the inspiration is almost the same, I think, with the classical integrability. So there's Lux operator valued Lux pair. That satisfy the same equation, but the difference is now our Lux pair is operator valued because we are in quantum regime, and yeah, we need operator to act to the system. And from this Lux pair, we can build the integral of motion, or in quantum we call it conserved charge, using the same equation with the classical. So what is conserved charge? It's actually the same with the classical counterpart. So conserved charge is an operator that satisfy Qi, the commutator of Qi and H is 0. We know that this is equal to TQi dt, and this is equal to 0. Yeah, we call it conserved because the derivative of the operator with respect to time is 0. I forgot to mention that this equation is called classical Yang-Baxter. Classical Yang-Baxter equation. And also in quantum integrability, we need that those conserved charges is also involutive. So we need that Qi, Qj is 0, and this statement is equal that we can find R matrices that satisfy quantum Yang-Baxter equation. Let me find the equation first. I forgot. R12 lambda 1 minus lambda 2 R13 lambda 1 minus lambda 3 R23 lambda 2 minus lambda 3 equal R23 lambda 2 minus lambda 3 R13 lambda 1 minus lambda 3 R12 lambda 1 minus lambda 2. So this is called quantum Yang-Baxter equation. Now, if we can find the R matrix that satisfy the quantum Yang-Baxter equation, then we can define monodromy matrix. What is monodromy matrix? Wait a minute. Oh, before that, we also can find the Lex operator L using the R matrix, and imposing the condition that the R matrix and the Lex operator satisfy this equation. As I state, we can define the monodromy matrix T equal and this monodromy matrix also satisfy equation that similar with the Lex operator, but we just change those L into T. If we have the monodromy matrix, then we can define the transform matrix small t, and it is equal the trace of the monodromy matrix. And yeah, this is false. Sorry. So in quantum integrability, the first quest or the first thing that we need to find is the R matrix. And if we can have the R matrix that satisfy the quantum Yang-Baxter equation, then we can find the Lex operator, and using that we can define monodromy matrix and the transfer matrix. And by using the transfer matrix, we can define the conserved charge. Which satisfy this equation log Tz Tz for exponentials L Q L Z L, which means we can find the Q using this equation. clock T set where Q is conserved charge. So in quantum mechanics, our goal is to find to calculate this equation, to solve this equation. So we have the Hamiltonian of the system and act it with any state, call it psi. Then we need, or we want to find this matrix or this value. But apparently it is not a easy task. So instead of solving this equation, we want to solve this equation instead. That means if we can diagonalize the transform matrix, then we can find the spectrum of the system. Because the H is contained in this T. Let us take an example. So we have Heisenberg spin chain. So it is a spin chain which the spin can be up or down, and with the specific boundary condition. In this diagram, I choose the periodic boundary condition. But we also can impose the open boundary condition. That's mean that yeah, it is not periodic, and yeah, it is just a line. The Hamiltonian of this system is yeah. Before that, each of the spin state described by the vector space V, which is C2, because it can have spin up and spin down. If we have spin chain with length L, then the Hilbert space of our system is just the V times L, or in our case it is C C2 times L, which is just C2 times C2 times C2 times C2 L times. So our Hilbert space is a finite dimension, which is 2 with the power of L, because because of that. And in Heisenberg model, the Hamiltonian, or the interaction of the spin, is just in the neighboring state. It means that only neighboring atoms that interacting with each other. So there's no interaction between this and this spin or atom. The interaction is just local. So the local interaction, we call it HKL. It is interaction between the spin K and spin L. Or we can write it by K plus 1, because it just interact with the neighboring. And the operator is, or the interaction is just this. And the full Hamiltonian of the system is the addition the summation of the local Hamiltonian, or local interaction. This Hamiltonian is called XYZ model, because the spin coupling is different if we have different spin coupling in each direction. But if we impose that the spin coupling between the X and Y is the same, but it is different with the Z spin coupling, then it's called XXZ model. And if we impose that all of the spin coupling is the same in each direction, then it is called XXX model. So XXZ model is just, we can think it as an XXX model that affected by magnetic field in Z direction. The XYZ model we can think of as a XXX model that affected by magnetic field in Y and Z direction. Before that, the R matrix here is also have the same characteristic with the Lex pair. I mean, there's no systematic way to find the R matrix. The R matrix and also the dimension of the matrix is not related with the dimension of the system. But if we can find the R matrix, then we can integrate the system, or the system called integrable. But luckily, people has already found the R matrix in X speed chain. It is something like this. And for the XXZ model, it is something like this. And using this R matrix, as we said, we can find the Lex operator that satisfy this equation. And after that, we can find the monodromy matrix and then find the transfer matrix. And then we can find the spectrum of the system. why this quantum integrability is famous, or many people doing this, because if we take the limit that the L is infinity, then the Heisenberg spin model, open Heisenberg spin model, is limit to 1+1 quantum field theory. And in quantum field theory, we are interested to find the S matrix, the scattering matrix, and it is found that the S matrix in the 1+1 quantum field theory is just the R matrix. And if the quantum field theory is integrable, then we can factorize the S matrix to just two-body system. I mean, if we have this Feynman diagram, then we can factorize it to this diagram that is equal with this diagram. And this diagram is just the Yang-Baxter equation. One, two, three here, 1, 2, 3 here. So recall that in Yang-Baxter equation, there are three indices here. So R12 is related with this. This is R13, this is R23. R12, R23, R13. And so it's easy to find the S matrix in 1+1 quantum field theory using the fact that the 1+1 quantum field theory is integrable. Okay, that's all my presentation. Sorry, because I'm not yet prepared it properly. And see you tomorrow.
Yo. Okay, that's the presentation from this student, this useless physics student.